Welcome to Mafia, a new podcast telling stories of America's criminal underworld.
Gotti assumed the position of head of the Gambino family.
And using the name Donnie Brasco, I was able to infiltrate the Bonanno crime family in New York City.
Bugsy Siegel is an American mob legend.
One man changed the whole texture and landscape of crime in America.
Listen to Mafia every Wednesday on Apple Podcasts or wherever you get your favorite shows.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again. Thank you for joining us on the Space Nuts podcast, where we talk everything astronomy in one episode, so you never have to listen to it again. And joining me, as always, is Fred Watson from the Australian Astronomical Observatory. Hello, Fred.
How are you doing, Andrew?
I'm very well. That's me, Andrew Dunkley. I didn't mention myself.
Let me introduce Andrew Dunkley, ladies and gentlemen, on the other side of this line.
Thank you, and good night.
Who, like me, probably doesn't even want to listen to it the first time, let alone listen to it again.
Anyway, for those who may be vaguely interested, today we'll be talking about atoms in your body that may come from galaxies far, far away. So I did it again, Fred.
Yes, you got it
the
in.
Star Wars reference in. Comets are bigger than we thought, some of them anyway, and there are many more of them, which leads us into a question from John at Minneapolis, which will finish us off today, because he's got a few comet questions for us. Or for you, I'll just read it out. But first of all, Fred, atoms in your body, or mine, or everybody's for that matter, maybe from galaxies from a great distance away. What are we talking about here?
Yeah, I think this is a very intriguing story because, as you know, and we've spoken about this many times before, most recently, I think in the last episode, the universe, when it was formed, was mostly hydrogen and helium with this mysterious dark matter in as well. But none of the common elements that we're so familiar with, the iron, silicon, carbon, oxygen, nitrogen, all of those things did not exist in the early universe. And we know that they were forged by nuclear reactions inside stars. So it's the stars that have created all these elements. It's actually the high temperatures and the nuclear reactions. So you start off with hydrogen and helium and you wind up with everything else. That's been, fairly well understood since the 1950s, 1960s. Fred Hoyle, one of the great names of astronomy, was one of the people who proposed that mechanism, and we now accept that is where the elements came from. So what it means is, this is where we all need to pay attention. This could be
difficult.
The raw material, I could just see you drifting off there. The raw material of our solar system, the rock that made the planets, the nitrogen that's in our atmosphere, all of that sort of thing has come from recycled star material. Joni Mitchell had it right. We're all stardust.
Yeah.
And in fact we are, because the atoms in our bodies indeed come from the same source.
I think I actually heard that same reference in a BBC documentary series called The Planets. They also made that claim.
What a spellbinding title! Well, it's true. That's where we're from. We're from. Our atoms are from the stars, but the current thinking has really been that, for example, when you look at the cloud of gas and dust from which the sun and its planets formed about 4.6 billion years ago, we've always assumed that they formed out of the debris of a previous generation of stars, and that is almost certainly correct, because you've got to have had stars before that for to find all the elements that we find. But we've always assumed that would have been fairly local, that it might have been a star at the end of its life that exploded in our vicinity, and the gas from that basically became the gas from which the sun was formed. It's what we call enriched interstellar gas. It's enriched by the processes of atom formation, what we call nucleosynthesis, to use its technical term.
Nice.
The synthesis of nuclei. And that's the standard picture. So the standard picture is that the atoms that came from that make up our bodies and our planet and everything around us actually started off in a star not very far from here. And that's what you'd naturally assume, you know.
Well, why would you think otherwise? Yeah.
Why would you think otherwise? Well, let me tell you, that's completely been turned up on its head by astrophysicists at Northwestern University in the USA, who have sort of looked at what they call intergalactic transfer. And it's asking about the question of to what extent does material flow between galaxies? And galaxies, of course, are aggregations of huge numbers of stars. We live in one with probably about 400 billion stars in it. So, and they're separated by enormous distances. So what these scientists are suggesting, and they've done this through fairly sophisticated numerical simulations. They basically build models of galaxies, of how they work and how they operate, and fast forward their formation from the Big Bang to the present time to see what happens. And it turns out that you get significant outflows of matter from galaxies, and it's driven by supernova explosions. These are stars perhaps 10, 20 times more massive than the sun that explode violently at the end of their lives. They eject huge amounts of gas into their locality, but they also basically set up winds of gas that can actually exceed the escape velocity of the galaxy. So you've got this outflow or breeze of gas. It's very, very rarefied gas, small numbers of atoms per cubic meter, but it's blowing from galaxies. And they suggest that it has the capability of blowing from one galaxy to another. So their calculations show that, first of all, that this flow tends to go from smaller galaxies and clusters of galaxies to bigger ones. And that's fairly intuitive because the gravitational pull of a bigger galaxy or a bigger cluster of galaxies is going to be more. But they also calculate that if you've got any given galaxy, up to 50% of the material in that galaxy can have come from another one. And that's far more than we have expected before. So the bottom line is that maybe half the atoms in your body have come from a galaxy far, far away, and have been blown along by the wind of material.
Any idea where? Have they pinpointed possibilities? Andromeda, maybe?
That is possible, I guess, although Andromeda's sort of closely bound to our own galaxy. And I think the suggestion maybe is that you might need to be looking further away. Really? Of course, if you're looking significantly back in time, which we are now, our sun was formed 4.6 billion years ago. If you're looking significantly back in time, then, of course, the universe hadn't expanded by as much, so everything was a lot closer together.
Yeah.
So maybe the trip was not quite as far as it will be today.
And, we can all look in a telescope into this distant galaxy and see our forebears saying, "Don't do it, don't do it."
Sadly, we did it. So
yeah, we apparently. Well, it is interesting. I mean, we've talked about transference between planets in our own solar system before. The swapping of rocks and things. So to consider that it's happening on a more universal scale probably isn't that big a stretch, really.
That's right. Exactly right. In fact, there's an example. I was at a talk about Pluto this morning by the principal scientist of the New Horizons mission, Alan Stern, which we'll talk about, I think, in a subsequent podcast. But he discussed the transfer of atmosphere between Pluto and its large moon Charon. So there's actually atmospheric transfer between the two, which again is the same kind of thing. It's gases moving from one body to another.
It's fascinating, yeah. And you know who else got all this figured out a long time ago?
I dread to think.
The makers of the animation Atom Ant. They
already
knew.
They knew. They knew things we don't know.
Indeed. All right. Well, there's obviously more to learn, as always with these discoveries. Questions are raised and more questions will need to be answered. So we might have more on this down the track. You're listening to Space Nuts. Andrew Dunkley here and Fred Watson.
Space Nuts.
Okay, Fred, this is a subject that seems to captivate people, and I believe we've got a question shortly from John on this very topic, and that is comets. And we've had questions before about comets. People seem to really have a thing for them. And you can understand it. They are fascinating. And now they think some comets are bigger than we originally thought. That's scary in itself, and we'll need Bruce Willis yet again. And there are more of them. How so?
So, yes, new observations by actually an infrared satellite, a NASA spacecraft, which has the rather elegant name of WISE. I think it's something like Wide Field Infrared Sky Explorer or something like that. I can't remember. It's a long time since. It's a good one, isn't it? If it's not that, it should be that. So it's basically an infrared space telescope, and by infrared we mean a telescope that looks at light that is redder than red, which is really heat radiation. So the great thing about the WISE spacecraft is that it can look at the whole sky. So it is very much a survey explorer, one that surveys its vicinity and counts the numbers of objects, or at least you do by computer when that's all returned back to Earth. And what they've done is they've measured more comets than they expected to. Why can you see comets with infrared? Well, comets actually show up quite well in the infrared, even though they are cold, icy bodies. A comet nucleus, which is the bit that sort of moves in orbit, is a few kilometers across. It's basically like a flying snowdrift with a lot of muck and dirt in it, which is the raw material from which our solar system was built 4.6 billion years ago. They actually are able to see these things very well with WISE. It's tuned perfectly to this kind of object. And what the scientists, once again from the United States, have discovered is that there are about 7 times as many comets over about a kilometre across. And these are what are called long period comets, and I'll explain that in a minute. There are about 7 times as many of them as we thought there were. And that's the great value of a survey instrument, because it lets you count how many things there are. Yeah. And we now know there's 7 times more. So a long period comet is one. The period is the length of time it takes to go all the way around the sun, and we call anything that takes less than 200 years a short period comet.
Like Halley's.
So. Yeah, Halley is a short period comet. That's right. So once every 76 years. So once every 200 years is the distinction between long period and short period. The long period comets are ones that we believe come from this hypothetical cloud of comets, which exists way, way out in the depths of the solar system. The distance is such that you can actually measure it in terms of the fraction of a light year to the edge of the Oort cloud. It's called that because it was proposed back in, I think, 1950 by Jan Oort, a great Dutch astronomer. And he said, well, where do comets come from? Comets that come in with orbits that are so stretched out, they must be coming from a very long way away. And he postulated the existence of the cloud, and that is still the accepted theory for where comets come from.
Well, Fred, he ought to know.
Oh, you ought to know. That's right. Oh, boom, boom.
Someone had to say it.
I think you ought not to have said it, actually. The Oort cloud, the source of long-period comets. So what we think happens is that these things, there's this shell of comets around the sun at this very great distance, best part of a light year or half a light year, something like that. As the sun goes round in its orbit around the centre of the galaxy, that cloud is disturbed slightly, and that makes comets, plummet in towards the inner solar system. So they appear as a long period comet, and then we believe they are often dynamically affected by the mass of Jupiter. Jupiter's a very massive object, and so Jupiter tends to pull them into a much shorter period, and that's how we think the short period comets come about. So Jupiter's influence in all this is very, very significant. But the new bit of this story is, as I've said, it's the fact that the long period comets seem to exist in much larger numbers than we thought, and they're bigger as well. They are more than a kilometre or so across. We used to think they were rather smaller than that.
Planet killers.
Well, they could be. They could be ocean builders, because one theory about where the oceans on the Earth came from is from bombardment by comets in the Earth's early history.
Could be.
So, yeah.
So you say there are 7 times more of these than we thought. 7 times how much?
Yes, 7 times a few. Look, it's I don't have those numbers to hand, but that is essentially the surprise of this research. I can bring up the paper actually.
Well, if it's 7 times 100, 700, that sounds manageable. But if there's like 1 million of them that we know of, seven times as many.
Okay, all right, here we are. Over the course of the 8 months of the survey, our results indicate that the number of long-period comets passing within 1.5 AU, that's 1.5 times the distance from the Earth to the Sun, are a factor of several higher than previous estimates, while what they call Jupiter comets, which are typically 20-year orbits, within the previous range of estimates of a few thousand down to sizes near 1.3 kilometers in diameter. In other words, the Jupiter ones fit the bill, but the long period ones don't. I can't find a number, Andrew. This is in the abstract for the paper itself. I'd need to read the paper.
Well, let's just pretend it's 1 and then we're all happy.
Well, it's a factor of several higher than previous estimates.
Yes, okay. Well, it gives us something to keep an eye on.
Indeed, that's right, as we do.
All right. You're listening to Space Nuts. Andrew Dunkley here, and of course Fred Watson from the Australian Astronomical Observatory.
What a matchup!
And what a team, Mike. Metro PCS and the iPhone SE for $0 on a network that covers 99% of people in the U.S. Oh, impressive.
Play with the best. Switch to Metro PCS and get a 32-gig iPhone SE for $0. Metro PCS. Coverage not available in some areas, plus sales tax and $10 activation fee. Claim based on talk and text. Not valid for active numbers currently on a T-Mobile network or active on Metro PCS in the past 90 days. See store for details and terms and conditions.
0G, and I feel fine.
Space Nuts.
To finish off, Fred, we're going to actually continue looking at comets because we've got a question from John in Minneapolis. Yeah, Minneapolis. And he says, hello, Dr. Watson and Mr. Dunkley. Should have been Sherlock. Anyway, that's okay. My name is John. I'm an avid fan of your podcast. Thanks, John. That makes 1. I have an inquiry about the Rosetta satellite and comets in general. I did a bit of reading from the solarsystem.nasa.gov website. They mention, as of 2010, astronomers have discovered about 4,000 comets in our solar system. Well, it's actually times 7 now, John. I was hoping you might have some more insight into how and why P67 was chosen as the site of the Philae lander. That's his first question. Secondly, how do astronomers differentiate between dead comets and asteroids? And lastly, do comets have the Oort cloud from the Oort cloud ever made their way to the inner solar system? I'd appreciate any information you have. Yes, John, we don't know. Thanks for joining us this week. And what do you think, Fred?
Well, look, we've just answered the last part of John's question.
We have.
Do comets from the Oort cloud ever make their way into the inner solar system? Indeed, they do. And that's where we think all comets come from. Just a footnote to that I didn't mention earlier, and that is that one reason why Jan Oort postulated that there's this kind of spherical cloud of comets around the sun is that when we see long-period comets, these ones that seem to come from nowhere and then disappear again, with a period of 106,000 years or something like that, when you see comets like that, they come in from all angles. They're not just in the sort of plane of the solar system. They come in from high angles, low angles, everywhere.
Yeah.
And so that suggests that their source, the reservoir from which these things come, is actually a spherical cloud. And that's what we still believe today, as I said, postulated by Jan Oort back in about 1950. So the question about actually what we might do is take John's questions backwards, because his second question is, how do astronomers differentiate between dead comets and asteroids? And indeed, there are such things as dead comets. So what do we mean by that? We mean one of these icy snowdrifts flying through space in which all the snow has basically evaporated. It actually sublimes, it turns straight into a gas and leaves just this rubble of dirt behind it. That's effectively what it is. It's just dust, which, of course, sticks together under its own gravity. So you've just got this flying rubble pile.
Yeah.
And that would be not much different in appearance from an asteroid, because it's something that doesn't outgas or emit gas when it gets near the sun. And by the way, it's usually, it's always the short period comets that do this, that become dead comets, because they're the ones, having come in from the Oort cloud, they get their orbits changed so that they are relatively short period, and that means they regularly go close to the sun, so all their stuff evaporates much more quickly, and they're much smaller objects than long period comets, which come in often for the first time from the depths of space. So that means, that dead comets do exist. How do you tell the difference? Usually by their orbits, because asteroids tend to have more circular orbits than comets do. Comets usually are in highly elongated orbits, even the short period ones. So that's really the main differentiator. There are some objects which sit between them. There are centaurs, which are objects that I think a centaur is half man, half beast, and these things are half comet, half asteroid. They come in once again with fairly elongated orbits, but generally it's the orbit that gives you the answer to John's question. How do you differentiate between the two? And finally, going to the first of his questions, I was hoping you might have some more insight into how and why Comet P67, or we usually call it 67P, that's all right, was chosen as the site for the Philae lander. And of course, it wasn't just the Philae lander, it was the whole Rosetta mission. Rosetta was a European spacecraft which took with it a little lander called Philae. Rosetta went into orbit, I think it was 2014, if I remember rightly, around comets Churyumov-Gerasimenko, otherwise known as 67P. And Philae actually landed on the surface of the comet, effectively crash landed because it couldn't grapple onto it and hang on as it was meant to do.
It was obviously designed by a professional pinball player, as it turns out.
Yeah, it was supposed to have grappling irons, but they didn't grapple very well. That was a problem. But actually, John, your question's well made, because 67P was not the first choice for the Rosetta mission. The initial project was to launch in 2003 to a comet called 46P, and its name is Virtanen. Comets they carry the name of their discoverer. Churyumov-Gerasimenko was discovered by two people, hence the double-barreled name. Virtanen was discovered by one person, whose name was Virtanen. But it's usually called Comet 46P. So that was the original target. This is a comet that they were going to try and rendezvous with as it made its way in towards the inner part of the solar system, so they could see the way the comet evolved and started outgassing and all the processes that were of great interest to mission specialists. Sadly, what happened was Europe had a rocket failure that set things back, and it meant that the mission was going to be postponed to 2004.
Missed the window.
They missed the window, exactly that. And that meant that...
Should have asked me, John.
Well, what?
No, carry on. Don't put me there.
No, I won't call you bluff there. I'll just keep talking. It meant that the mission launch was postponed to 2004. It meant that had they stuck with Comet 46P at that late stage, there would have been, the rendezvous would have been too late. It would have been taking the spacecraft too far away, and they wouldn't have seen any of the activity on the comet. So they looked for another target, and sure enough, they found Comet 67P Churyumov-Gerasimenko, and the rest is history. The launch took place in 2004, and it was a fantastically successful mission.
Yeah, by the way, despite the problems, we got a heck of a lot of data and learned a lot about comets, or this one in particular, which they're still sifting through, I imagine.
Oh, I think that's right. There's still a lot of data. The spacecraft itself, Rosetta, was crashed into the surface. When I say crash, the speed was 2 miles per hour, but it's enough to probably damaged the spacecraft because it didn't have any the Philae. The lander had legs to land on, but the Rosetta orbiter itself didn't. It sent back this was in September 2016. Sent back images of the close approach, and I think we will see still more data coming back from Rosetta, or data that came back, which is currently being analysed and reanalyzed to produce more scientific results.
Okay, John, I hope we satisfied your inquiry. Thank you for sending your question. And we certainly do encourage you to send questions to us, because we might even be able to answer one or two every couple of years. But that just about wraps us up for another episode. Thank you, Fred.
A great pleasure, Andrew. Always good to talk.
And you too. We'll catch you again next time. And thanks for listening to Space Nuts. Don't forget to follow us on Facebook and Twitter. We're on your favourite podcast platform. And don't forget our sister podcast, Space Time with Stuart Gary, which is also available on Apple Podcast et al. But until next time, from me, Andrew Dunkley, it is goodbye for now.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.
Welcome to Mafia, a new podcast telling stories of America's criminal underworld.
Gotti assumed the position of head of the Gambino family.
And using the name Donnie Brasco, I was able to infiltrate the Bonanno crime family in New York City.
Bugsy Siegel is an American mob legend.
One man changed the whole texture and landscape of crime in America.
Listen to Mafia every Wednesday on Apple Podcasts or wherever you get your favorite shows.